Hello everyone, welcome back to my channel. In this video, I'm going to talk about the closure of a set in a topological space. So let's get started. We begin with a definition of the closure of a set. Given a topological space X and a subset omega of X, the closure of omega is defined as the intersection of all closed sets that contain omega. And this is the mathematical formulation. In order to better understand this concept, we are going through a very simple example. In this example, X is the set consisting of three elements A, B, and C. And tau is this collection. We can show that tau is a topology on X, and therefore X with tau is a topological space. In this topological space, we consider three sets, omega 1, omega 2, and omega 3 given over here. Then my question is, how can we find the closures of these sets in this topological space? In order to find the closures of these sets, it is very important to know the structures of closed sets in this topological space. It is quite simple because there are only four open sets in this topological space. And please remember that a set F is closed if and only if its complement is open. Therefore, in order to find all closed sets in this topological space, we only need to find the complements of these open sets. Let's work on that, okay? The complement of the empty set is X. The complement of this single point set is this set. The complement of AB is C, and the complement of X is the empty set. Therefore, all closed sets in X are four sets over here. Okay, let's work on finding the closure of the set omega 1. Okay, this is the set omega 1. So, we're gonna look for all closed sets that contain B, this single point set. Okay, so X is a closed set that contains omega 1. This set BC is also another closed set that contains omega 1, and that's all. Okay, therefore their intersection is this set. So the closure of omega 1 is this set. Similarly, there are two closed sets that contain omega 2. They are X and this set. Their intersection is this set. And in this example, you see that the closure of omega 2 is itself, okay? And observe that omega 2 is a closed set in this topological space. Finally, the closure of omega 3 is here. The closure of omega 3 is X, because X is the only closed set that contains omega 3. Okay, next we are going to talk about some important properties of the closure. Let X be a topological space and let omega be a subset of X. Then, the closure of omega is always closed, and omega is a subset of its closure. How come the closure of omega is closed? By definition, the closure of omega is the intersection of a family of closed sets. This is the family of all closed sets that contain omega. And as you know, in a topological space, the intersection of an arbitrary collection of closed sets is closed. Therefore, the closure of omega is closed. Okay. And how come omega is a subset of its closure? Please remember that in this collection, every set F contains omega. So their intersection contains omega as well. Therefore, the closure of omega contains the set omega. The second property says that if F is closed and F contains omega, then F contains the closure of omega. So, how come this is true? If F is closed and F contains omega, then F is one of the sets we consider in this collection. Therefore, their intersection must be a subset of F. Okay. Therefore, the closure of omega is a subset of F. The first and the second properties tell us that the closure of omega is the smallest closed set containing omega. Again, the closure of omega is the smallest closed set that contains omega. There is one more property I want to present in this theorem. Omega is closed if and only if omega is equal to its closure. How come this is true? We can prove using this definition. We also saw one example of this property from the previous slide. Now, I'm going to explore more properties of the closure. This is an important one. Let X be a topological space and let omega be a subset of X. Then an element A belongs to the closure of omega if and only if for any open set V containing A, we have that the intersection of V and omega is non-empty. Let's look at this example in the Euclidean plane R2. This is the closure of omega. And this element A belongs to the closure of omega because of the following reason. No matter what open set V we take, and V contains A, then the intersection of V and the set omega is non-empty. It is similar for B and C. They are elements of the closure of omega, and again, no matter what open set containing this point, the intersection of that set and omega is non-empty. In the setting of a metric space, we can actually replace open sets in the previous theorem by open balls to have this theorem. Let X be a metric space and let omega be a subset of X. Then A belongs to the closure of omega if and only if for any r greater than 0, the intersection of the open ball with center at A and radius r with the set omega is non-empty. Again, let's look at this example in the Euclidean plane R2. This element A belongs to the closure of this set because no matter what radius r we take, the open ball centered at A with radius r intersects the set omega. Okay, and similarly for B and C. Now, let's work on an example. In this example, the set X is the entire real line, and the set omega is the interval from -1 to 6. Depending on the type of topology we consider on X, the closures of omega could vary. Let's look at the first one. Let tau 1 be the usual topology on X. In X with tau 1, the closure of omega is the closed interval from -1 to 6. We can prove this using the definition of the closure. At the same time, you can also use this theorem to show that the closure of omega is this closed interval. Tau 2 is the discrete topology on X. Please remember that in this topological space, every set is both open and closed. In particular, the set omega given here is closed. So the closure of omega is itself, which is this interval. Okay, next we will look at the trivial topology or the indiscrete topology. Tau 3 consists of the empty set and X. In X with tau 3, there are only two closed sets. We can get them by taking again the complements of these sets. So the only closed sets in this topological space are X and the empty set. So the smallest closed set that contains omega is X. Therefore, the closure of omega is X. Finally, in this example, let tau 4 be this collection of subsets of R. It consists of the empty set X and all symmetric open intervals of this form. Again, in order to find the closure of omega, it is important to know the structures of closed sets in this topological space. So the complement of the empty set is X, the complement of X is the empty set, and the complement of each open interval like this is the union of two intervals. From the interval, the union of minus infinity to minus alpha, union alpha to infinity, where both minus alpha and alpha are included. We can easily see that the closure of omega is the entire space X. Okay, please work on it at home to verify that we have this property. Finally, I have one question for you. Let X be a metric space given A in X and R greater than 0. Is it true that the closure of the open bond centered at A with radius R is the corresponding open closed bond? Okay, so my question is, in the setting of a metric space, is it true that the closure of any open bond is the corresponding closed bond? The answer is not. This is not true in general. Let X be R and let D be the discrete matrix on X given by this formula. I'm going to put a link on the description below so that you know more about this metric space. In this metric space, the open bond with center at A and radius 1 is a single point set, while the corresponding closed bond is the entire space X. In this metric space, every set is both open and closed. So, in particular, any open bond is closed. Is that weird? Okay, so the closure of this open bond is itself, so it's a single point set, while the corresponding closed bond is the entire space X. They are not equal. So this is a counterexample for this property. Later on, I'm going to talk about norm vector spaces. Okay, and it's very interesting that in a normed vector space, this property is true. So let's see that in my future videos. Okay, so that's all. This completes my video about the closure of a set in a topological space. Thank you for watching.